Okay, good morning again from my side, and I will now start the second introductory lecture to today's and tomorrow's networks. Purpose of my presentation and lecture is to give an overview, basically, of the topics that will be much more in detail discussed in the following lectures, and trying to build an overall picture around, which is somehow the strategy that involves at the same time the different projects I mentioned, so RESERVE and Sogno. In a bigger picture, I have some reference to what also Professor De Donca said, because the DC part is one element of that large picture that is basically the main research agenda of my institute that is then implemented in the project that we are currently involved in. First of all, I'd like to clarify a very important change of mentality that is happening, because that's affecting a lot of things. I don't know how much are you familiar with the game of the cloud word. The cloud word is this tools, software that there are some free online. They take a document, parse the document, and try to identify frequency of use of a certain terms. So if I was doing a cloud word, this is a real one from document 3 years ago. Smart grid was a dominating topic in our field. Everybody was doing smart grid. If you were not doing smart grid in power system, you were out. So it was the main buzzword that was going around the power system community. And I think partly is still the truth, but I think there has been a change recently, and I'm involved in the ETIP SNET activity. ETIP SNET is a platform of the European Commission for driving the agenda of research in 2030 to 2050, and we recently wrote one document on the technology that are driving this process. So what I did, I used one of these online tools, and I did the cloud word myself, and it turned out that smart grid is not anymore dominating that document at all. There are some, if you look around, it is also there, but digitalization is the new big topic that everybody is addressing. And then the question is just that every 5 years we need to change the buzzword to keep it fun, or there is also a change in mentality and philosophy in what's going on? And I like to think about more the second version, because the first one is a little bit too depressive. So what's the meaning of this change? First of all, what is digitalization? Digitalization is not only a factor that is affecting the energy sector. It is a broader thing. This is a kind of a definition that is also in that document. Is the process of moving to a digital business that is using digital technologies to change business models and provide new revenue streams and value-producing opportunities. What is immediately clear in this statement compared to smart grid is the moving the focus simply from upgrading an infrastructure to changing business models. So that's the basic change has been happening recently, is that is not only about putting some more sensors in the grid, interconnected ICT and energy. That's what was smart grid, but that was mostly a technology-oriented way of thinking. Right now, we are moving more and more in determining which kind of business model use case will drive this change. Digitalization is not all happening in energy. What is peculiar of energy, though, is that we are going through this transformation like many other business sectors while we are completely transforming the sector itself. And this is making the energy case a little bit special. So in that sense, the digital energy network paradigm is a broader concept of smart grid with significant social components and focused on service. So that's what is my interpretation, at least the consideration about this change of buzzword from smart grid to digitalization. I would say probably if you look at the US, it's still smart grid widely used compared to how much is used in documents in European context. And I think because the change in the business sector from the business point of view is less disruptive in the US than what it is in Europe. So in Europe, we have been going through, we're still going through a significant change of the landscapes of the companies that are driving the energy sector. And some of the large companies that were present are still but they're a totally different company. You see that in the logo of our center, we have the name of a very large German utility, E.ON. I think E.ON is a very good example of this change. If you compare what E.ON is today to what E.ON was when they started a cooperation with us, you will find there are two totally different companies. And that's the sign how this process in Europe is much more than making the grid smart. And that's why we need a new terminology. In this working group, I mentioned that I encourage you to visit the website of ETIP SNET. You can download a very large document. What we did as an exercise was to look that the digitalization affects 3 layers. So this is, maybe you're familiar with this picture, is used 300 times in presentation, is the famous SGAM, Smart Grid Architectural Model, that been defined by the European Commission a few years ago to formalize how you define a use case in the transforming network. It involved 5 layers from component, communication, information, function, and business. In the ETIP SNET document, in trying to understand this process of change that we call digitalization, we decided to cluster a little bit and say, okay, there is a physical layer part. A physical layer deals mostly with topics like the one Professor De Donker mentioned before, what's changing actually in the way electrons flows. This is the really physical layer. One example, DC, but I'll bring you others. Like I'll try in my presentation to be as broad as I can in that sense. There is an infrastructure layer that is more what people call smart grid, basically. So how the grid automation is changing, that's where mostly my institute is working. And then there is the business layer, which is how the business is changing and how, like I said before, large utilities are now a completely different company from what they used before. Professor De Donker explained like how large power plants are becoming a burden for some of those companies. Like E.ON completely got rid of their power plants, but also the Italian large utility Enel, probably one of the largest in Europe at least, did the same. They tried to sell those this part of their business and to focus on completely new scenarios. And at the end, and that fits with the introduction I made at the beginning, the real focus is moving more and more towards customers. And that means we move from providing energy to provide services, which is really a revolution for the energy sector. Here, starting now, I want to start from, like I say, from the physical layer, as you saw, using the equivalence of the communication. And I have here something that I used before, and then De Donker also referenced in his presentation. Just a little game, but now after we talk already, probably the game is not so powerful. You know this guy? You don't know this guy? Oh, come on. Who knows this guy? Edison, great. Yeah, he's Thomas Edison. Why I like this? This is a famous story that also De Donker refers to. He had a view for the system, that the system was supposed to be based on small power plants. He was working mostly with low voltage, and he believed in distributed generation. That was his view, and he convinced investors that was the big revolution that was coming. We are talking about the end of the 1800s, and like the energy development, the electrical development was like internet was basically in the 1890s. The big business where everybody wanted to be part of. And he convinced a guy called J.P. Morgan, so not a small person, in the business, that this was the vision and that he knew how to make large business out of electricity. And J.P. Morgan realized the first home completely electrified to convince investors to invest in the Edison company. That was a big revolution. Get away from gas. Electricity is safer, is better, and we do it at home. You have a little power plant at home, and you generate your electricity, and you're fine, independent. That was the view. Who is this guy? This is less famous as Faith. That's Westinghouse. That's the sad part of the story, I would say, because I'm an electrical engineer, nothing personal, but he's a mechanical. What's the problem? That he had a different view, and without being an electrical engineer, he thought that we should go for AC current and talked about big power plants, push the voltage high to increase efficiency, and lamp generation as much as possible. Anyway, that's the sad part of the story. The mechanical engineer had it right for the time, and then came a guy to help him, Tesla. Yeah, I'm glad you're the generation that still knows that Tesla is a person. I made this similar presentation in the elementary school. They told me, what? Tesla is a car. No, actually, he's a person first. So he's a very important scientist. And then the company used the name. That's a little bit sad. And they realized, this was in my first slide, the first ever power plant. And the purpose of this power plant was to connect Niagara Falls, the first serious installation of electrical energy, to the city of Buffalo in New York. There was the first industrial park in which energy was not distributed through mechanical complex systems, but through electricity. And so good news, at least, was the first power plant was green. And that set up the scene. And from there, the AC, as the Donker said, won, mostly because at this competition, Westinghouse showed that he could raise the voltage just outside the power plant in Niagara, transfer the energy, and reduce for safety close to the loads. And what these guys brought to the picture, that Westinghouse had a big problem, was he didn't know how to convert the electricity back in mechanical. And then the induction machine, that was controversial invention, because if you're Italian, you believe Ferraris created this, but the Ferrari was not a business guy. He didn't make a patent, so it didn't pass to the history. While Tesla was smarter, made a patent, but then he was fooled by Westinghouse. They used the patent without paying him any dollar. So at the end, the mechanical guy got it right also in the business sector, because he convinced Tesla, look, I have a little bit of problem in my company. Is it okay if I don't pay you royalties? And Tesla, oh, it's okay. And then they signed the contract. That's it. Gone. And he became rich. The other didn't. So the two electrical engineers get fooled, and the mechanical became rich. And then, because the disaster at the end of the story, Edison also lost his company, because JP Morgan was kind of upset and shut down the company, kicked Edison out, and created General Electric. So JP Morgan made it right as well. Good. So what we learned from there is the main point, that at that time we went for AC for a very simple reason. There was no alternative. That was possible because we didn't have a transformer. And then the power plant with lamp generation brought another interesting element we cannot forget. So the AC also had the advantage that with a large generation rotating machines, that brought us that large inertia. They make the power system a kind of a slow system. And that allows us to decouple. That's the way, the principle of the overall automation in power system is that the large masses are slowing down the transient enough that you can control with these thermal systems. And at the end, when you write dynamic of a power system, not of a network, but of a power system, the equation we write, the so-called modal analysis, doesn't even care about the electricity part. It's just a constraint. But the dynamic is only coming from the rotating mass. So every generation, in principle, when you do modal analysis in power system dynamics, brings two state variables coming from the rotation of those masses. So those rotational masses that generate the AC are the trick at the end that keep the system together. And then because of that, we went for a highly interconnected system to increase reliability, and that's been the concept. So we developed the most complex infrastructure. We have to be proud of it. I mean, particularly the European interconnected power system is the largest human-built infrastructure working together. And around the concept of synchronous operation and based on extremely efficient communication channel, because that was the last trick. Frequency was not only a variable, is at the end in the current grid a communication channel. And I always challenge my friends in the ICT technology, can you build me something as efficient in communication as we have right now using frequency? Because as you know, the frequency is used to map the power imbalance. so that without any measurement, distributed or a complex infrastructure, the control room knows exactly the overall picture of the grid in one quantity. This is genius. And the fact that people didn't have all the sophisticated ICT that we have today, had to think twice before going for a solution, and going very simple. So that's the complete structure that altogether justify the system we have. We need AC for the transformer. We have the advantage of the large power plant to keep the system moving slowly, which is nice, easy for the automation or control guys like eigenvalues which are slow. And the third is, by the way the control is built through the famous primary, secondary, tertiary control in a power system, we associate frequency, delta in frequency, to delta in power. And that means the control room knows in one quantity the global status of a complete infrastructure. This is the starting point, and we have to keep in mind that it's extremely smart. So that's one of the reasons I never liked the term smart grid, because the term smart grid came more from the ICT people, and they're like kind of thinking that the power system was dumb. The power system was extremely clever because it was built on a it is still today, built on a very simple principle that was not requiring to do what maybe we have to do now. So it's arguable if the smart grid is really smart. And that mapped also to the way that we are been using the infrastructure for about 100 years. And then is, okay, if I concentrate my power plant here, all on the top, strange, these slides are not exactly the final version. Okay, doesn't matter. The power plants are here. I interconnect the power plant through a transmission network. For redundancy and safety, I build that network as meshed because I want to always have an alternative to use every power plant I have. So I need a mesh network. And then I built the overall distribution network as a passive infrastructure. And what is clever here again is that if you look at the kilometers of line, there is a big difference between transmission and distribution. Contrary to the intuition that you think transmission long distance, then long kilometers. If I take an example of Italy, the transmission network of Terna, which is the single operator of the transmission line, is between 20 and 30,000 kilometers. But Enel, which is one of the distribution system operators, even if dominating, manage 1.3 million kilometers of line. What it means that automating 20,000, I get to work 1.3 million. Again, the architecture was designed in a way that was extremely simplifying a very challenging task. And the distribution network was built radial because the purpose was only from the main load center to ship energy to the end customers. So very simple position, very easy. And that's the legacy we have. That you think about what the Donker also say about mesh versus radial and the role of DC in that context. Power flow then was supposed to go always in this direction. So from the transmission network to the distribution network. And then this was, as a hypothesis, a passive infrastructure. So that's main key point. The generation is highly concentrated, system is quasi-static, so that we don't care about writing differential equation for the electrical grid. The generation is totally under control, that was the idea, and the loads are statistically predictable. I lumped in this big load center, and I minimize my uncertainty. I can predict quite well my load scenario for the next day, and that allowed me to schedule the power plant, and the control and automation are only to make correction. It's not about the big position, so that you know from the statistics of the load, you know basically how much you need in transmission, you can allocate to the power plant, and then obviously prediction are always somehow, but only somehow wrong, and then the control, the automation, primary, secondary, tertiary, primary, secondary control, are there to adjust, tweak the system, which make the system also not exposed to very large transient in principle, not unpredictable, but because the major steps are envisioned a priori with the scheduling that are coming. So you don't really need to manage in a strictly real time. In real time, you correct small error. Small is kind of vague concept. The flow of energy is from transmission to distribution. And distribution is intentionally totally passive. So this was the way we run for about 100 years, and we were able to interconnect the system. Then comes the story. Then there's some curve to give the impression how renewables are rapidly expanding, close to exponential growth. Big impact in wind in Germany. Yesterday, probably even too much. And at the same time, volatility. So these are the key elements that the renewables are bringing. This is a real measurement of the contribution of wind a few years ago, 2007. So it's still old, if you like, but still I like to keep it because in 2007 we can move from 17 gigawatt to 0 in the contribution. So it's like you have a 17 nuclear power plant, sometimes connected, sometimes not. That's not nice. 2007. So go figure what is today. Solar PV, big change here. There was a nice year when the Renewable Act in Germany made extremely convenient to install PV on the roof. People were covering their roof with PV because it was an easy business case at the beginning, and that created this ramp in the 2005, 2010. Now it's not growing as much. It's been mostly then law-driven. Now the German government has been reducing the so-called in-feed-in tariff gradually year by year to bring it close to something that is not anymore so convenient. Right now, the in-feed-in tariff is lower than the tariff you pay to buy, and this is vice versa since a couple of years, incentivizing in Germany a market of battery system, because you sell energy for 15 and a couple of hours later you buy for 30 cents per kilowatt hour. Then you start calculating and you end up finding that battery starts making sense for many people at home in Germany. Assuming you don't live in Aachen, because probably, as you saw, the weather here is not really motivating. But in large parts of Germany, the weather is not as bad in Aachen. Probably, I'm sorry guys, this is probably the worst place in weather in the whole country. So don't blame Germany. That's not the average. That's probably the worst. Some numbers. So what is this trend meaning? Because one thing is on curves. I'm kind of trying to give the facts behind. The total renewable contribution in energy for the electricity last year reached about 30%. So Germany is already beyond the 2020 target. What is interesting is that it's already happening that the in-feed has been over the load of that given moment. So we had moments in which the in-feed for renewables was like 110% or 105% of the load, which means, making happy the Dutch, we were selling energy from Germany to the Netherlands at very low price and buying from the Netherlands a few hours later for double the price. But that's Dutch business. And but that says, even if the total contribution is 30% of energy, I'm an automation person, I'm caring about power. So I don't care if the problem is only 1 minute or 1 hour in the year or 1 day. I have a grid in where that penetration renewable is possible today. So we should not get confused by the statistics that says we'll be 100% renewable in 2050, because in 2020, let's say, we already have scenarios in which the penetration renewables is extremely high to be sure that the energy-wise will be at that level in 2050. So there is a difference between I'm looking at the CO2 market, I'm looking at the energy market thing. This is one part. This is my colleague, Professor Moser. One thing is I'm doing the automation, need to keep the grid stable. The challenges are already here today. That's why the question we look at reserve, that we talk about 100% renewables, is not just future, is tomorrow morning. We had also some interesting points, again, when we look at what is changing, is that we had a couple of times during the weekend, okay, the low was lower, but who cares? That's the system we had at that point. We had 50% of power coming from PV in low voltage all over Germany. That means that the idea that the stability of the grid was connected to large power plant was quite shaky for about an hour. Nothing happened. Good. But from an automation point of view, we have moments in which the grid is significantly under stress. And I'll show you more results, but real data about how that is really changing all over Europe. And we are moving then more in this direction, in which we are talking a lot about distribution because reserve is focused on distribution, but we don't forget we need transmission. This transmission is still there, is a key element. That's why in the picture, this picture, I'm sorry, I put the credits, but they disappear in the slides. That comes from the University of Aalborg. I want to give credit. And the transmission line is in the middle because it's still a key infrastructure, but we have much more complex constellation of elements in the system. We have more role of PV, we have role of wind, we have sector coupling as another interesting element that is transforming the grid. So the system is totally different already today. And here sort of a comparison present future, well, let's say future sometime is today. We move from generationally concentrated to a more distributed generation. We move from a system that is quasi-static to a system that has higher dynamics. We move from a system that is totally under control, that a system that is highly affected by uncertainty and unpredictability of the generation. Show you the slides with numbers. And that means we move from a system that is basically load-driven. We calculate the load, we know the load, and then we steer to a system that is more and more generation-driven, which is then currently changing the role, and I'll talk about that, or what the load should be and how the load should behave. The power flow used to be unidirectional from distribution transmission. In a situation like the one I told you before, 50% from PV, the power flow was going in the opposite direction of what the system was designed for. And the distribution is not anymore passive, and we have a higher dynamic and low physical inertia. So there is the inertia is like the first line of defense of the system, and this is shrinking the more we substitute with power electronics, at least if the power electronics is used in the way has been used at the beginning for the introduction of renewables. And that would be one of the major points of discussion. So classical grid is based on real-time balancing. That's the way it was done. Doesn't make sense in renewable grids. And when we move to this scenario, we see that to balance the uncertainty and the variability here, we need flexibility on the other side. This is the new big topic in the grid. If the input is changing, we need to balance the equation. The grid has no storage intrinsically, so we have to create architecture. What are the needs? Currently available resource for flexibility in Europe have been estimated by the European Commission to be 20 gigawatt. Theoretically available, but we don't access today. There are 100 gigawatt already, but they estimated by 2030 we'll actually need 160 gigawatt of flexibility. So if we consider the trend in the generation, the volatility those are bringing, those are the numbers that we need on the load side, or combination, because sometimes load and generation are together, the so-called prosumer, to balance the system instantaneously. And this is really challenging the fundamental point. How do we get to match this number? And this is only 2030. So if you go higher, the flexibility we are looking for will be even higher. And that means that we bring at the center the customer. This is where the flexibility, where customer is intended in a very wide sense. I like this picture. This comes from NIST, the standardization body of the United States. What I like about it, this picture was done about 10 years ago. And they already figured that the customer was not just going to be the guy paying the bill. But it shows a very complex data and energy flow between customers and the infrastructure that we were not used to, and that is coming. And first element of flexibility everybody talks about, all the demand response, demand side management, and involving at the grid level. This is discussed but is not really coming for the moment. That's quite interesting. There are not trivial problem in building a business case, building interest in the customer, first of all. One statement I like, but by my colleague at Baum Consult, which are our experts working in the Sonia project for the dissemination activity, and Ludwig Karg, which is the CEO of the company, always says, have you ever asked a customer if he's interested in flexibility? And you figure, I mean, if you're not an electrical engineer in these things and you ask about somebody's flexibility, you know, well, what? Why should I care? This is the big difficulties behind those things, concepts that are possible, technically speaking, to unlock more flexibility. One thing is technical, one thing is socially. That's why I said, beginning, the digitalization in creating new business cases, not just a technology challenge, is a social challenge, because we need to overcome this. The same for the e-mobility that Donka already discussed quite intensively. I don't need to cover myself. And bring in all the interconnection and dual communication between the customers and the grid is anyway one of the key elements to begin in this pattern. So those are the premise. What can we do? And when we look at the system level, and we have seen the challenges, we have seen this flexibility. Now, using the same structure of the ETIP SNET document I mentioned, I'd like to give some reference on options, basically. So if I compare to 100 years ago, they don't already say DC would be possible. So it's something we need to put in the picture. And then, on the other hand, the role of the inertia, how we bring this concept together. One thing is, as I say in my first talk, I don't see power electronics as a problem. I see power electronics as an opportunity. Why? Because while in the traditional grid, we rely on the physics of the synchronous machine to provide the response we need, here we have the freedom to define control law that will fill the requirements that we want. So it's a complicated problem because it's open, but we have the freedom and the option to rethink the system in a way that is totally open. So we should look at this situation as an opportunity, as a problem, because we have new degrees of freedom. That's, to me, the value that power electronics brings, and how we insert new mechanism in the current grid is one of the biggest challenges. So I look at those degree of freedom in three categories. We have frequency as a degree of freedom, voltage as a degree of freedom, interconnection as a degree of freedom. What does it mean? What we are doing in different projects is to experience and validate what can be done in frequency control and the way we intend frequency, what we can do at the voltage, and last but not least, it's not a secondary, that I will cover very briefly, but not secondary from the value, what we do with the interconnection. So we give as granted right now that the way we run the system as totally interconnected and energy flowing freely all over Europe is the solution. And the power electronics open different way of thinking also in that context. So let me start with frequency first of all. We have two options. We can ask ourselves, should we stay with AC? And my colleague De Donker will have a clear answer, no. You heard clear reasons behind. I will briefly touch because he can do that much better than me. But also if we stay with AC, we have to ask ourselves how to make use of the flexibility and the programmability, let me say, of the power electronics in a smart way. So AC versus DC, I'm using slides from the flexible electrical networks where the Donker already introduced, and he already mentioned all the good things. Clearly DC is simpler. That's the appealing part that nobody can argue with. It's easier to create something constant that try to shape a nice sinusoidal waveform. The sinusoidal waveform were coming naturally out of rotate, well, naturally. ask a guy working in electrical machine design. But let's say at the end, with very good design, we were creating a nice sinusoidal waveform. Not easy, but we managed through the years to make it quite nicely. But if we do that from electronics, that's not immediately straightforward. And these are all the advantages that the Donk already mentioned. I'm referring to his pictures again on how it can be actually seen as something that helps the current infrastructure. I like this slide because many times the DC versus AC is placed again in like a word of current, like the Tesla situation of 100 years ago. What I like about this proposal from the Donker is that it shows that you can actually find a way to coexist, and DC helping without saying we don't need AC anymore, because we have a huge infrastructure. It's unthinkable to just trash overnight for a new solution, but you can think of progressively upgrade the system, and that's a nice way to start in that direction. And the same with his idea of city quarter completely working on DC. What he didn't, I don't remember his mention because actually 5 minutes the meeting, but that we at the university, all the chairs involved in these topics are actually building that scenario, creating a DC network in our campus. There will be an overlay network at 5 kilovolts that we will manage to learn, because one of the major problems with DC currently is lack of experience, also for the manufacturers. So if we have a playground where we can learn together, that's the idea of our Fusions campus that the Donka mentioned before. We have many more opportunities to de-risk the technology, make the manufacturers confident and the grid operator confident. Yeah, we have to keep in mind the grid operator are rightly so very conservative. People are always accusing the grid operator, you're too conservative. Yeah, but at the end, they have a big responsibility. When you have a blackout, you get really upset. And you would not be willing to say, oh, yeah, thank you, but you were testing the new technology. That's fine. You just don't like blackouts. So that's for the DC part. But what if we stay AC? You will hear later a follow-on presentation on the topic, actually a couple of presentations. But why do we have to rethink anyway? Well, what's going on in a nutshell here is that with the change of, mostly related to the change in inertia, the frequency signal is changing a lot. It's changing a lot in the dynamics, it's changing a lot in the peaks, and these are real diagrams of real measurement of frequency, real grid. These were not the kind of transient we were used to see, so that's kind of an alarm signal. We're still able to manage those, but it's kind of like bringing the system to the limit. And that means that we need to imagine different ways to interact with the system so that we get more support for the frequency, faster access to the support. And what is also interesting is that the frequency also that we have been, I would say at the beginning, it's a great communication channel, is also losing part of that characteristics because the local frequency sometimes is significantly different from what it can measure at different locations. So we don't have all the time a solid single frequency because the transients are so violent that you have challenges in defining what frequency is. That's mostly the work our colleague in University College of Dublin have been doing on understanding how to look at those local frequencies versus global frequency, how to assess the behavior. That's a transient. That doesn't run for some reason. That should be a transient measure on the, that's the trick. That shows frequency as function of position. This was calculated by our colleagues in Dublin. And you see that you hardly can define a global quantity during transient. This is the 8-bus IEEE system, been slightly modified to increase more penetration renewables, but give a picture of how some fundamental principles are currently under pressure. And these are some real measurements. Again, that was a simulation. You may argue about it. That's, for example, using an interesting grid that we have the pleasure and the luxury to use in many experiments, the Irish grid, in which we compare local frequency versus the frequency measured from the transmission system operator. We see significant changes and not perfect matching. And why is Irish very interesting case? Not just because one of my assistants is Irish, Barry McKeever, and that is sitting there, but because Ireland is somehow like looking in the future. It's an island, obvious, but it's an island from the electrical perspective because they have a weak connection to the rest of the system. They have a very high penetration of renewables, mostly based on wind, and this wind is mostly located in one coast, which is the west coast. What that brings is a system has all those characteristics of weak inertia that have been mentioned before, the high volatility of generation because the penetration of wind can be extremely high, and not the luxury to be like Germany, that whenever we have excess or defect, we go to the Dutch, we go to the Polish, French, plenty of friends around. And the Irish grid was supposed to be reinforced, connecting to the UK, but unfortunately the UK decided not to be anymore in the European Union, and then the funds of the European Union are not going to build that link anymore. So now the new plan is to connect Ireland to France, which is, when I look at the map, crazy. But that's some present from the UK. And but that means also that before Ireland could have a more robust system, we'll go even more through the transformation and be more under stress, for example, when it comes to frequency control. A few years ago, in another European project, again in cooperation with ESB, the distribution system operator in Ireland, we did a very interesting study of what if a storm comes from the west coast. And it turned out they will lose so much generation at the same time. So because when you get a storm, first you have wind, so you have a lot of renewables coming in. Then when the storm pick up, the wind is too strong. You lose all of a sudden all this generation. And if you're an island, all of a sudden you have no resources. There is no time to bring up the thermal power plant. And so the only solution was to find a very fast demand-side management program. ESB was interested to understand if electric vehicles could be the solution for that problem. Because again, Ireland is interesting also from the electric mobility point of view because it's so small that you can travel all over with a car of today. So you don't need a very complex infrastructure or whatever. It's small enough that the modern electric vehicles will make it. So they have a very aggressive program as well. What it turned out that bringing the right value of inertia and everything, if we didn't have a very efficient demand-side management program, so the communication time that you need from the event at the TSO level to informing the operator of cars, and the car sending the signal and shutting down, assuming everybody was charging, which was still an optimistic view, it was not possible with the infrastructure they had at that time for communication. Why? Because the frequency peak coming down was so violent that some of the power plant will trip. And then you have a typical domino effect. And that simulation was unfortunately verified the year after, where they had a major blackout in one part of Ireland, exactly following the pattern that we envisioned with that study. Okay, that's about Ireland, but that's Germany. So that's a famous event that happened in January here in Europe. There was a frequency disturbance in France. France used to be extremely robust and still not completely clear. The first information that were delivered is that the event happened at the change of the hour. So it's normally then when you have the change of the hour, you have peaks, the same we have seen the Romanian grid. This is connected to the market because we have a lot of generation enter and some other leaving. That change, create a little bit of shake to the system. Apparently, one justification was an unlikely event of contemporaneity in operation. But somebody also envisioned that probably there was also a measurement mistake somewhere in the power flow, I think, between France and Spain. All of a sudden, anyway, the whole European networks got this glitch, very strong in frequency. This was measured by us here in our substation, where we have some PMUs installed. And this was measured by own PMU also in Italy. So quickly, this frequency disturbance spread all over Europe and showed that dynamic are not the one we are used to at continental level. So it's another alarm. The French were pretty good. RWTH saved us. We were able to shut down loads enough to compensate for this frequency drop rather quickly. So their action was more efficient than what was a few years ago in Ireland. Obviously, the grid is bigger, so it's more sturdy. But those are alarms that are ringing. And that brings to the idea, will be just in the next presentation discuss, the frequency control concept has to evolve to involve distributed energy resources and going in a more decentralized way. But we can think also in two other advanced options. And one is the so-called self-synchronous network. This is an idea that has been appearing in literature and still under investigation. It's more like forward thinking. That's something you can use tomorrow. And the other point is, at the end, if we stay with AC, even if we change the mechanism of frequency control, we need to involve in this game the distributed energy resources, and that brings to the idea of virtual inertia. The self-synchronous network, it's a very interesting system that has been proved. I'm here give credit to the first paper I'm aware of. In our field, there was the group in Illinois, Urbana-Champaign, by Professor Krein. What they developed is the idea that there is in the chaotic system, the oscillator tend to, nonlinear oscillator, to find an equilibrium point and resonate with each other. And you can mimic basically this physical phenomenon in your control and developing some oscillator behavior in your control. That's an example where you have a linear part of oscillation and a nonlinear function. And that creates this behavior, which allows to bring, this is a little bit of mathematics, but later you'll get more details, and I don't want to get into the details here. I'm just giving this overview. And it's been proved in small network as an easy way to put together different sources and keep the frequency stable. Here in the give and take, that's a very interesting way to keep frequency stable, but we lose somehow the usage of frequency as a communication channel. So we have an advantage because we don't have this violent transient anymore in the frequency, because frequency plays a different role. That's nice. And on the other hand, is not playing really the role it's doing today. So it's again not something you can introduce day and night. We've been working with this problem. That's a reference to our work, and extending the method to be sure that in any case we are able in this game to manage dispatch. So we define in this nonlinear oscillator what kind of contribution of active and reactive power a given generator will bring to the system. So that allows to have a real control of dispatching on power electronics systems. We don't need inertia anymore in this case, basically, because the system finds naturally to converge, is attracted to a point of oscillation as a nonlinear system. This has not been proven on large scale for the moment. The whole concept and ideas are most looking things like microgrid. We have been working on inserting one of those sources in a major grid, but not assuming that the whole grid will work this way for the moment. But that's, an opportunity, because we don't have any more synchronous machine, then frequency can be used as a quantity in a completely different way. That's basically the message. And this is possible. And now there is already quite some literature on the opportunities. And for sure, this is a solution that in small scenarios like a microgrid is extremely appealing to avoid deal with complex primary, secondary, and so on control. And so as a role immediately anyway. We also been exploring other ideas that this oscillator can also bring other ancillary service to the grid. So it's quite flexible, more flexible than what it looks like when you look at the first applications. So it's an interesting direction. The other idea is vice versa, to stay AC and basically keep the logic as before. And then people, many authors here, I'm referring to a paper from Norway, the group at SINTEF, led by Dr. Darko. They've been proposing an architecture to control and creating the so-called virtual inertia behavior. And that's the idea that if you have some storage of some sort in locally, whatever it is, that storage basically plays the same role of the rotating inertia, as long as you control, mimic with equation the behavior that that inertia will have. And this been done in many different versions, and people use a different terminology because of different architecture. Some people talk about virtual synchronous machine. When you try really to emulate completely the dynamic of the synchronous machine, they use about the term synchroverter. But they all, bottom line, come to the concept to use the power electronics system level, so you don't touch anything here. So the voltage control, current control is classical. But then on top, at the system level, you schedule the power injection following, in a virtual way, the behavior of a rotating mass. Oops. In this concept, what we have been doing in reserve, you will hear a full presentation by Professor Reitz later. Okay, if we have to do something of that type, we don't have to be to bring in also the negative part of synchronous machine. So synchronous machines are nice to bring the stability, blah, 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 but they're also the reason of the wide area oscillation in the system, because the equations, when you look at the nonlinear characteristics at the end of the power injection, can bring to oscillation. Now, thinking with the idea that power electronics is an opportunity, can we think more freely on the way this process is done? And that's why we come up with the idea of linear swing dynamics. So finding a way through the control to get behavior of the source perfectly linear in a wide range. Obviously, there is always a point where nothing is linear, but getting to have a very, as much as possible, wide range of operating point for a generator acting on the grid such that the eigenvalues are fixed. This brings a fantastic consequence, because it means from the grid operator point of view that the dynamic of each elements are highly predictable, independent from the operating point. So you don't need to have modal analysis for every condition of operation of the grid, but there is one constellation of eigenvalues, and that could be, at the end, a grid code. If you want to be connected dynamically, that's the way you should behave. And as long as you linearize your behavior, you can be linear dynamically, the better you approximate this ideal situation. And here will be a way of compromise. So we're still preserving frequency as a communication channel, different from the nonlinear oscillatory game, but we try to make our contribution different and trying to use the power electronics to get something better than the physics of the synchronous machine. Here, again, a little bit of the equations, but I don't need to dig into those because that would be the presentation later. But this has been by us demonstrated, and we have been developing strategies, and I think this is a kind of a topic that is a beginning, and you can follow that mentality and come up with many different solutions. We have here some example of schemas, but later Professor Rice will give you much more than what I can do now, and this is just to show it's really true. You see this change and always see the same dominating eigenvalue and the transient, that is that linearity effect that you want to get. And here you see on the bigger picture that you move over a linear characteristic between power you inject and angle with respect to the grid. So this is possible. It's an opportunity, it's an option that brings a different way to look at how the inertia can be contributed by power electronics. Okay, that's it for frequency. Now again, voltage. Also voltage is I don't know, again, can say issue if you like, but we have to rethink. Why? Because we've been focusing only on the 50 hertz, but now that every device in the future will imply power electronics, we need to get a bit broader in our understanding of the dynamic of the system. Again, I will briefly touch this later. Sriram will give you a complete overview. So on one hand, the power electronic stability becomes a problem that is over a wide range of frequency. That's wherever the control is active, and you have interaction between the different. So it's not about the single converter, but it's about the interaction among converters that we have to learn more than what we are used to. On the other hand, this can be done because we can shape the behavior of the power electronics response over frequency. So it's not an unsolvable problem, let's say. And what we are doing is to use some theory that in power electronics being quite popular in the power supplies where they had to develop cascade of converters since a long time, PC feeders, for example, and they had to manage the problem that when you connect to power electronics in cascade, you have this interaction that emerges, and so the two control are basically not independent. This has been studied from the beginning from a famous theorem from Middlebrook that if you are in power electronics, you should know quite well. And then studied further in other study here, I'm referring to a work done at University of South Carolina in the US, where they've been looking at that concept quite intensively. And when you look at voltage, basically in the reserve, we are looking at from two perspectives. We have the steady state condition, so the slow moving problem, having different sources spread over the network. But under dynamic condition, we have this interaction that may bring to unexpected oscillations. These are some experiments, and we have to understand how to deal with them. And so what we are looking at in the project, and Sriram will present, we are reviewing the idea of impedance, talk about wide frequency impedance, and understanding what kind of information we extract. Well, first of all, how we extract that impedance from the measurement perspective, and how we use that information to make a system that is more robust from a voltage stability point of view. Here are some examples of the system we are looking at. This a lot of work has been done in harmonic stability at University of Aalborg by Fred Blaiberg. So it's some reference again to give complete overview literature, not just what we do. And that's what we are looking at right now, is how from different points of the network we are able to identify those wide frequency range impedances and how the control should keep that into consideration. And this again will be also that's another interesting reference that I like to give you from the group in NTNU in Norway from Professor Molinas. They're looking at similar concept. And the process in two steps. We have a wideband system identification because you don't have this information available normally, so you have to be able online to extract, but this is technically feasible, and that means a converter should be able to have this functionality in this view to understand better the grid where it's connected. And then there's the way this process can be done. We use PRBS signal, pseudo-random binary signal, to do this identification process. And then with the results of the impedance, this can be used in the monitoring and operation of the grid, also getting maybe support from the substation for the computational perspective if this is not envisioned in the grid at the beginning. This is not my final version. Okay. Yeah, last point, and then I'm closing in time. Interconnection as degree of freedom. Here again, I refer to work from other authors. This is mostly the work, the leader in this group, in this type of topic, Professor Lisere from the University of Kiel, here in Germany, on the role of the so-called smart transformers. What the idea of smart transformer is that even stay with AC, you may imagine to have a power electronics driven substation, obviously very flexible to move in the future to DC, because internally you see the DC-DC converter that the Donker presented. And what's the advantage is that if you imagine to embed here also some storage in the DC side, you decouple the section of the grid from one from another, which means on one hand, you don't have anymore a uniform frequency signal all over, but at the same time, you break the paradigm of contemporaneity all over the infrastructure because each section can be balanced independently thanks to the role of the storage in the substation, maybe combined with storage at the customer level. This type of view means the grid do not need to be fully interconnected in the classical sense. So not interconnected in the sense of free flow of energy from among the level, which means we could be much more open to frequency deviation because there could be totally a local issue that is not creating stress at a voltage because it could be confined totally maybe at the low voltage and doesn't propagate because the frequency on this side is not the frequency on that side anymore. And this is an interesting degree of freedom in my view. And each grid becomes an island that combined together may offer service to the higher level. So the grid get a compact whole here in the substation. Here you have control. You can decide how you feed and infeed with respect to the rest of the infrastructure. This open a different paradigm of contemporaneity and synchronicity with respect to what we have today. Yeah, what we're doing that's a little bit more on the automation side. This was the overview. All in all, we'll need more measurement. This is bringing the need for more low-cost sensor to instrument the low voltage and medium voltage grid. This is a reference to another project where we have two companies, one called MAC, an Irish startup that developed very low cost for sensor for low voltage, together with Altea producing vice versa advanced sensor for medium voltage grids. So there are new type of sensor emerging that fits the requirement of distribution system. We need new concept of substation automation that will be more discussed in the following day, like when you will hear from Marco Pau, I think that's on Thursday, on the different service that can happen in the substation. We had a project called Ideal in which we look at detail of the architecture. And we are doing these things directly in our campus. That's why we had the measurement I mentioned before. We did this also in real test field. So this measurement that can help are being tested, for example, in the grid of ESB in Ireland. And they learned a lot about what's going on in the grid, particularly when you look at the unbalance of the system and way beyond what they expect. So they have way higher losses. And we verify the same in Germany. And that brings to the link to the project Sonio that also probably will be briefly introduced better by Marco Pau on Thursday, and how this function can be virtualized in the grid. And last but not least, the role of the communication infrastructure in achieving this picture, 5G in particular. What is interesting about 5G is that with the edge concept, you decouple the local traffic from whatever goes to the main network. This is critical not only for the response time and the reliability of the response time, but also from the point of view of data security, because data may stay local in the edge, not going into the overall core network as they will do today. And that's what we investigate together with Ericsson. You hear a lot about this concept tomorrow and Friday by the expert of Ericsson that will join us. I'll bring it to the cloud. Cloud means right now also another level of challenges in terms of managing data. I call it like a Babylon cloud because there's a lot of problems still going on in data semantics that have to be addressed to allow this picture, different way to intend cloud infrastructure platform or software as a service. And we have been involved in some large European effort like the fiber concept to standardize. This is the critical point to enable this view of flexible automation in the cloud to get real European level standard. And the Fiber Foundation is an example in that direction that we explore in a variety of projects, test field in Europe, coming to a general architecture with real use cases. For example, this in Sweden on cooperation with E.ON, or building a full microgrid in Denmark that we had together with our partners in those projects. We are still working in this area with a project called FISMAP, trying to expand the standardization and the standard type of services that can be offered in a cloud or in the project SONIO. The very last things about the wide testing. So with all these ideas and automation, how you convince a grid operator that makes sense, what we have been working on is creating a lot of open source tools that can be used by, first of all, other universities. We are developing a real-time simulation platform based on dynamic phasors that is going to be released very soon as an open source, which allow you to do simulation in the range of some milliseconds and in real time on standard PC, so you don't need to buy expensive hardware if you don't need to go into the microsecond. But for the large system, this is good enough for also to interconnect different systems. That's a good level of details. We need a little bit of shade there. It doesn't last long, the sun in Aachen, don't worry. If I find the right. And we're also developing, in cooperation with many other research institutions, a framework to connect laboratory to build very, very large scenarios of studies. This is what we call VILLAS, Virtual Integrated Laboratory for Large System Simulation. We are working with many universities right now in Europe to use this solution of architecture to connect laboratory and perform very large real-time experiment. We had one real case of large scenario in collaboration with the United States. We ran 8 laboratories together, 6 in US, 2 in Europe, simulating a global grid. That's basically the plan of China state grid to interconnect at continental level. So the European JRC and the Ministry, the Department of Energy in the US asked us to start working together because we will be interconnected somehow. And so we had San Diego National Lab, National Renewable Lab, Colorado State University, Idaho National Lab, Washington State, the University of South Carolina on this side, and Politecnico di Torino and our lab to manage a large experiment of simulation real time using our technology VILLAS. This is again an open source solution. We are now working with many other research groups in Europe to try to use this as a common ground where groups can work together. We are currently installing in cooperation, if I think is DTU and in Denmark and Delft here in the Netherlands. They're working with us. We already have Romania involved. We have Ireland. So Italy is already with Torino, but could be other labs involved. Austria with the Austrian Institute of Technology. So this is a network, and this is totally open source. We'll be happy to cooperate and work together on these things. That's finally the end, 5 minutes too late, my presentation. I will now stop recording, so you're also more free on asking questions. You don't have to worry about the recording part. Thank you.